Hey everybody. Okay, so in this video we're going to be reviewing the dot product. So if you take a look at these two vectors in space, u and v, you can always move a vector around as long as you don't change its magnitude or direction, right? So I can pick up vector u, move it over here. I can pick up vector v, move it over here. So if you have two vectors and you already know them in terms of their components, one way to compute the dot product is dot. You just take the x component times the x component, right? Plus, and then this y component times y component, z component times z component, and that's it, right? The answer is a scalar, right? So vector dot vector is scalar. Another way to compute the dot product, let's say you already know the magnitude of this vector, you already know the magnitude of this vector, and then you see how there's an angle between them. Well, technically there's also this angle, right? So the smaller angle between them. The other way to compute the dot product is this magnitude times this magnitude times cosine of that angle, the smaller angle between the two vectors, right? So two different ways. Okay, so here's an application. Let's say you have this vector in space, but you want to decompose it in a way that it's one component parallel to some line and then the other component normal, right? Because you can decompose some vector, let's say u, into two components. One component that's parallel to a line plus the other component normal to the line. So this becomes really useful. And then to do it, first we need to define this line. So to define it, we'll just define some unit vector along the line. Right, so that's how we're gonna quantify the line. So then if we want the component parallel like this, it just goes like this. So the component of the vector parallel to the line is E dot U. Almost. This is a scalar, right? This is only the magnitude. The direction is this way, right? This way. This way. Right? This is the direction. Right? And then if you want the other component, we already started with the vector we knew. So if you want the other component, just subtract, right? Move this on the other side of the equation. Okay, so that's how you decompose. Let's do an example here. So let's say we want the component of vector let's say some position from A to B. So we make a vector going from here to here, this way. What's the component of that along this line? Okay, so first we need to define that line, right? So we define some unit vector along the line. no problem, right? So from A to C, the position is 14 minus 0. We'll just write 14 minus 0 in the I direction. 0 minus 7, the J direction. 14 minus 0 in the Z direction. Right? But for a unit vector, we need to divide by its own magnitude. Okay, so we got the unit vector along the line. Now, let's say we want vector, this position vector from A to B. So from A to B, 0 minus 0, and then 0 minus 7, and then 10 minus 0. Okay, so that's vector, the position vector from A to B. So now we want the component of the position vector along the line, right? So if we want the component, then it's I'll call it parallel. Right, then it's E dot R. Right? Well, that's the magnitude. Right? That's the magnitude. The direction is this unit vector. Right? So for that magnitude, let's just show a little bit of work. Right? So then you just take, let's see, so the x component, 14 over that should be like 441, right? This x component times this x component times this x component plus this y component, negative 7 times this y component plus this z component times this z component, right? So then this is some scalar, and that is this number, right? And then this is this. Okay? Alright, thanks for listening. I'll see you on the next video.